Hey, I'm Noggs, and this is Noggs House. Today we are going to talk about the formation of the Milky Way and our solar system. We're going on an amazing journey to learn about our cosmic origins, where we came from on the biggest scale possible. We're going to explore how our home galaxy, the Milky Way, was born and grew over billions of years. Then we'll zoom in to see how our own sun formed from a cloud of gas and dust about 4.6 billion years ago. Finally, we'll discover how the planets in our solar system came to be, from the rocky worlds close to the sun to the giant planets further out. Understanding these origins helps us understand our place in the universe. We're not just sitting on a random rock. We're part of an incredible cosmic story that stretches back nearly to the beginning of time itself. We'll trace this journey from tiny particles floating in space all the way to a fully formed galaxy with billions of stars, and from a collapsing gas cloud to our solar system with all its planets. So let's get started. Our home galaxy, the Milky Way, started forming about 13 billion years ago. That's only about 800 million years after the Big Bang. The early universe was a chaotic, messy, and disorganized place filled with gas and dust floating around. Most of this was still hydrogen and helium from the Big Bang, but it also included some heavier elements made by the very first population 3 stars we talked about earlier. Through gravitational infall, that's when gravity pulls material inward towards denser regions, this dust and gas started clumping together. As more and more material fell in, it started rotating, spinning. This rotation is really important. When a spinning cloud of gas collapses, it naturally flattens out into a disc shape, kind of like how pizza dough becomes flat when you spin it. That's why most galaxies, including the Milky Way, have that flat, disc-like structure. But there's a secret ingredient that's crucial for galaxy formation: dark matter. Dark matter is mysterious, invisible matter that we can't see directly, but we know it's there because of its gravitational effects. Dark matter formed huge halos, that means spherical regions or shells, around the forming galaxy, acting like gravitational anchors that held everything together and helped regular material fall in and collect. As the Milky Way was forming, the first stars began to light up inside that what astronomers call a proto-galaxy. That's just a fancy word for a baby galaxy that's still forming. These earliest stars were metal poor, meaning they had very few heavy elements, because they formed from gas that came almost directly from the Big Bang, with only small amounts of enrichment from the very first population 3 stars. Many of these ancient stars still exist today in the galactic halo. That's the roughly spherical region surrounding the main disk of our galaxy. They're also found in globular clusters, which are tight balls of hundreds of thousands of old stars orbiting the galaxy. About 13 billion years ago, the thick disk started to form. The thick disk is a layer of older stars that puffed up thicker than the main disk of the galaxy. Between about 13 and 8 billion years ago, the Milky Way went through a turbulent, wild, and chaotic era with intense star formation. Huge numbers of stars were being born, living, and dying. When massive stars died in supernova, they scattered heavy elements throughout the galaxy, slowly enriching the gas with metals. Remember, in astronomy, metals means anything heavier than helium. Here's something really cool. Our Milky Way didn't just form peacefully on its own. It grew by eating other galaxies. The process of something growing by absorbing other things is called accretion. Over billions of years, the Milky Way has had several major mergers with dwarf galaxies or smaller galaxies. Scientists have discovered evidence for some really important collision events. The Kraken event happened about 11 billion years ago when a gas-rich galaxy merged with the young Milky Way. This brought in lots of fresh gas for making new stars. Between 7 and 10 billion years ago, there was a massive collision called Gaia Enceladus, also known as the Gaia sausage. It's called sausage because of the stretched out orbits of its stars. This merger was huge. It scattered stars throughout the halo and triggered a major burst of star formation. There was also the Sequoia event, which brought in stars on retrograde orbits. That means they orbit backward compared to most stars. These collisions weren't gentle. They were violent cosmic smash-ups that actually helped shape the Milky Way's structure. Scientists think these mergers even contributed to forming the barred spiral structure we see today. A barred spiral means the galaxy has a bar-shaped concentration of stars in the center, with spiral arms sweeping out from the ends of the bar. At the center of the Milky Way is the central bulge, a thick, bright region packed with stars. This bulge formed relatively rapidly and contains both very old stars from the early days of the galaxy and surprisingly young stars that formed more recently. Around this bulge, the thin disk formed later than the thick disk, from gas that had been enriched with heavy metals from earlier generations of stars. The inner thin disk formed from residual gas, that means leftover gas, that remained after the earlier bursts of star formation. This thin disk, where our sun lives, is flatter and contains younger stars with more heavy element. The Milky Way today is a beautiful barred spiral galaxy about 100,000 light years across. A light year is the distance light travels in 1 year, about 6 trillion miles. It contains somewhere between 100 and 400 billion stars, all held together by gravity and dark matter, spinning through space as one massive cosmic structure. Now let's zoom in from the whole galaxy to focus on just one star, our sun. The sun formed about 4.6 billion years ago, which is actually pretty recent in galaxy time. The Milky Way is almost 3 times older. According to the nebular hypothesis means an educated guess based on evidence. This one explains how solar systems form. The sun was born from a giant molecular cloud. This was an enormous cloud of gas and dust floating in one of the Milky Way's spiral arms. The cloud was mostly hydrogen and helium, but unlike the first stars, it also contained heavier elements like carbon, oxygen, iron, and silicon, all the metals that had been made and scattered by earlier generations of stars. But something had to trigger this cloud to start collapsing. Giant molecular clouds can float around peacefully for millions of years without forming stars. Scientists think our cloud was disturbed by either shock waves from a nearby supernova explosion or powerful stellar winds from massive stars. There's actually evidence for this. Meteorites contain an isotope called iron-60, which is only made in supernova and decays fairly quickly. Finding it in old meteorites suggests a supernova happened nearby right around when our solar system was forming, and may have been the trigger that started everything. Once the giant molecular cloud started collapsing, amazing things happened fast. As the cloud collapsed inward under gravity's pull, it also started spinning faster. This is because of something called conservation of angular momentum. When a spinning object gets smaller, it spins faster, like how ice skaters spin faster when they pull their arms in. As it collapsed and rotated, the material formed a solar nebula, a giant spinning disk of gas and dust with most of the mass concentrated in the center. That dense, hot central core became the protostar. Proto means early or forming. So a protostar is a star that's forming but hasn't started fusion yet. The protostar kept gathering more and more material, getting hotter and denser. Eventually, after about 100,000 years, the core temperature reached roughly 10 million Kelvin, hot enough for fusion ignition. Hydrogen nuclei started fusing into helium, releasing tremendous energy. At that moment, our sun was officially born as a star. The newborn sun contained more than 99% of all the matter in the solar system. It's absolutely dominant, with all the planets, moons, asteroids, and comets making up less than 1% of the total mass. While most of the material went into forming the sun, some remained in the disk orbiting around it. This leftover disk is called a protoplanetary disk, a disk around a forming star where planets will eventually form. At first, this disk was mostly gas with tiny grains of dust mixed in. Over time, these dust grains started settling toward the middle plane of the disk, kind of like how sediment settles to the bottom of a lake. Once concentrated there, the dust grains began sticking together through electrostatic forces. That's basically static electricity, the same force that makes your hair stick up after you rub a balloon on it. Tiny grains clumped into bigger grains, then into pebbles. The pebbles kept growing through collisions until they formed planetesimals, objects ranging from about 1 kilometer to hundreds of kilometers across. Think of planetesimals as the building blocks of planets. There are 2 main ways planetesimals could have grown so fast. One is called streaming instability, where pebbles concentrate in certain areas of the disk and suddenly collapse together. The other is direct collapse, where pebbles drift inward and pile up, directly forming larger bodies. Either way, within a few million years, the disk was full of planetesimals ready to build planets. The inner part of the solar system disk, close to the hot young sun, had very different conditions than the outer parts. Temperatures were very high, often over 1,000 degrees Kelvin. At these high temperatures, something important happened. Different materials condensed, changed from gas to solid at different distances from the sun. Silicates, rocky materials like the minerals in sand and stone, and metals, like iron and nickel, could condense even at these high temperatures. But volatiles, materials that evaporate easily, like water, methane, and ammonia, stayed gaseous and couldn't freeze. This meant the planetesimals forming in the inner solar system were rocky and metal-rich, but deficient in or lacking volatiles like water. These rocky planetesimals kept colliding and sticking together through accretion. As they grew larger, their gravity got stronger, letting them pull in even more material. Eventually, they became protoplanets, almost planets that were big enough to start pulling themselves into spherical shapes. Through countless collisions and merger over tens of millions of years, these protoplanets became the terrestrial planets, the rocky worlds Mercury, Venus, Earth, and Mars. Terrestrial means Earth-like or rocky. Out in the outer solar system, beyond a boundary called the ice line, also called the snow line, things were very different. The ice line is the distance from the sun where it's cold enough for volatile materials to freeze. Generally where temperatures drop below 170 degrees Kelvin, about a negative 150 degrees Fahrenheit. Beyond this line, it was cold enough for water, methane, and ammonia to freeze into ice. This was a game changer because it meant there was suddenly way more solid material available to build planets. According to the core accretion model, our best theory for how giant planets form, planetesimals in the outer disk could grow much faster because they had all that ice in addition to rock and metal. These icy rocky cores grew rapidly, and once they reached about 10 Earth masses, something dramatic happened. They became massive enough to start capturing the surrounding hydrogen and helium gas directly from the nebula. This gas accretion is how gas giants Jupiter and Saturn got their thick atmospheres. Uranus and Neptune are ice giants. They have rocky ice cores, but less gas because they formed later, after much of the nebular gas had already dispersed. But here's something wild. The planets didn't stay where they formed. Through planetary migration, planets can actually move inward or outward from their original locations. Type 1 migration affects smaller planets, while Type 2 migration affects giants. The Grand Tack model suggests Jupiter migrated inward towards the sun, then reversed course and migrated back outward, like a sailboat tacking, dragging Saturn with it and drastically reshaping the solar system. What an incredible journey we've been on today. We started with the birth of our entire galaxy, the Milky Way, about 13 billion years ago. We watched as dark matter provided the gravitational scaffolding as the first stars lit up, as dwarf galaxies crashed into our growing galaxy and helped shape its structure. We saw how collisions and mergers weren't disasters but actually helped build the beautiful barred spiral galaxy we call home. Then we zoomed into about 4.6 billion years ago and watched our sun form from a collapsing cloud of gas and dust, triggered by a nearby supernova. We traced how gravity pulled material together, how rotation formed a disk, and how the sun ignited fusion in its core. Finally, we explored how the planets formed from the leftover disk material. Rocky terrestrial worlds close to the sun where it was hot, and giant planets further out where it was cold enough for ice to form. We learned how temperature, gravity, and chance collisions all played crucial roles in creating the solar system we know today. Scientists continue to refine our understanding through observations from telescopes, analysis of meteorites, and computer simulations that recreate these processes. It's amazing to realize that all of this, our galaxy, our sun, our planets, came from the dynamic cosmic forces of gravity, collisions, and chemistry. Thanks so much for hanging out with me at Nog's house today. Next time we're going to talk about something even closer to home, the birth of our own planet Earth and how it became a special world that could support life. I really hope you'll join me for that. See you next time.